Okay, in this section 8-5 we are continuing on with looking at vectors. And so in this particular section, the first thing we come to is kind of a review of some of the previous sections where we can write a vector in linear combination form by taking its magnitude and multiplying it by the standard position vectors with these angles, and then that way you can come up with this part would be your A, this part would be your B, and you can write it in linear combination form this way. Of course, you can transfer that back to component form. We've seen that. And then, of course, the value of the A and the B can be used to find the angle if it's missing. Through here is the progression. So this part is the B part, this part is the A part, and then that's the same formulas that we kind of looked at and discussed from last time, because we're going to be using these now in order to answer questions like this. Okay, let's say that we have a quarterback that's running forward at 5 meters per second. He throws a football with a velocity of 40 meters per second at an angle of 25 degrees with the horizontal. What's the resultant speed and direction of the pass? Right? And so we have two vectors at play here. Right? We have the trajectory and velocity at which he throws the ball. That's one vector. But he's also running forward, so that's another vector, right? So those two vectors together would produce a resultant vector that would actually give the speed and direction of the pass. So how do we figure it out? Well, first of all, let's make sure that we know our first two vectors. So the first vector we'll call V1, all right, we know is him running forward, right? Well, let's write that vector out. It's 5, 0, right? Because he's running forward at 5 meters per second. Okay. Now, the second vector we can also find, but we're going to have to do a little bit of work to be able to write it in actual numbers of component form. But remember, how can we do it? So if I wanted this component, then I could just plug it into this formula. Remember, this is the magnitude times the cosine of the angle, right? The magnitude times the cosine of the angle, right? And so really the magnitude, remember, of the second vector, he's running at 40 miles per hour. So that would be, or not miles per hour, meters per second, I should say. So that's 40 times the cosine of 25 degrees. Okay? And the other component then, right, because remember that's this component, the magnitude times cosine of the angle, that's the first component. The second component, the J component, is going to be, again, the same velocity, 40, but times the sine of 25 degrees. So that would be the I component. Now, remember, this formula is actually given in linear combination form, and I'm writing it as component form, but remember, it's the same difference, the same thing. This part is your I part of the linear combination form, and this part is the J part of the linear combination form. So it is the same thing. Okay? So now I can just calculate the value of these, and then I can get the second vector in the same form as the first vector. So let's see if we can. So V2 would then be equal to it would be, let's see, come here to the calculator, make sure you're on degrees. Remember, it automatically defaults to radians, so you're going to have to switch that over. We'll go 40 times cosine of 25, and so that's 36.25. And for the other one, I just need to change that to sine. And then that's 16.9. All right. So that's the component form of the second vector, just written in regular old number form. Okay. And so again, remember what we've got here. The vector has a horizontal component of 36.25 and then a vertical component of 16.9. So that's all I've done here. Now, how does the ball react as a result of these two vectors? And remember, when we're looking at this is actually speed that we're looking at for this first component, right? Let's see. Okay, so if I want to get the resultant vector from this, then what I need to do is I need to add these two vectors, vectors 1 and 2, together, okay, to see how the vector of the throwing angle and velocity and the running, which is straight, and velocity, how does it affect the way the pass comes out? And so here's the resultant vector. Add 5 to this and get 41.25, and add 0 to this, and we stay with 16.9. All right, so there's the resultant vector of the trajectory of the ball, right? This is the resultant vector of the trajectory of the ball. Now, what are they asking us for? What's the resultant speed and direction? So we need the resultant speed, which means I need the magnitude of this vector would give me the resultant speed, right? So we need the magnitude of r, which would give me the resultant speed. How do I find magnitude? Square root of 41.25 squared plus 16.9 squared. All right. So let's see what that turns out to be. So we will go clear that off. I need square root. I need 41.25 squared plus 16.9 squared. And then there's my resultant speed, which is 44.58. 44.58. And of course, we're talking meters per second is the unit. Okay? So that is the resultant speed of the pass. Okay? So if he throws it with a velocity of 40 meters per second, at the same time he's running forward at 5 meters per second, the ball is going to come out at 44.58 meters per second. All right? At that angle of a throw. Okay? So even though he throws it at 40, because he's running forward, he gets a little bit more speed out of the ball when it actually comes out. Okay? Now, that's not the only thing they want. They want the direction, which means we're going to have to find the angle here. Well, how do we do that? We come back to this. So it's going to be tangent of the angle is going to be equal to B over A. Well, what's the B? 16.9. And what is the A? 41.25. So now I've got an equation that I can solve for the angle. Do the inverse tangent to both sides, and we'll end up with the angle being the inverse tangent of 16.9 over 41.25. Okay? Calculator finishes that up for me. Okay, we are still in degrees, I believe. Yep, so we're good there. So I'm going to go inverse tangent of 16.9 over 41.25. All right, Darion, that's you. So 20. Yeah, just leave it there. I'll get it. Yeah, because you won't be coming back, I don't think. So 22.28, that is the direction of the pass. All right. Did you finish the quiz for here? Yes, sir. All right. Good deal. Okay, so this is the resultant speed of the pass. This is the resultant direction of the pass. All right. Let's try another one. Okay, this one's a little different scenario. So in this one, we're talking about flight path of a plane. And so let's say we have an airplane traveling due east, okay, with a speed of 600 miles per hour. The wind blows at 65 miles per hour at an angle, okay, of south 52 degrees east. Remember, this is a bearing, and we haven't looked at bearings for a while, but remember, it starts with the south, the north-south component, and then it gives you a degree measure east or west. So that's the angle 52. So that's the angle that the wind's coming at, 52 degrees off of south. All right. So it's going 600 miles an hour, traveling this way, but the wind is blowing this way at 65 miles an hour. So the question is, what's the speed of the airplane's flight? Because it's going to get a little bit of a boost from this. It's not, the wind's not exactly behind it, but it's still going to boost it a little bit with 65 miles an hour pressing onto the plane there, and determine the angle of the airplane's flight. So it is going to push it off at an angle a little bit. It's not going to be going due east anymore. It's going to be traveling a little bit off because of the factor of the wind there, the wind speed. All right, so let's see if we can figure this out. Once again, I need my two original vectors, and the first one here is going to be 600, 0. All right, and so it's traveling east, right, at 600 miles per hour, and it's not traveling anywhere north-south, so that's 0. For the second one, we'll calculate just like we did on the other page. Okay, it's going to be, now this other vector is the wind vector, right, the wind vector. Well, remember, what is the magnitude of the wind? That's what we need first. The magnitude of the wind is 65, all right, and then followed by cosine of the angle. Now we got to be careful here with the angle, because we're not going to use 52 as the angle, right? We've got to use the angle that's made by your vectors, right? Got to use the angle in here is what we want. But I can get that by doing 90 minus 52 and recognizing that that's 38 degrees. So 38 is actually the angle that we want that's made right there between the two vectors. Okay, so that's the angle that you want, not this one out here, because you're not using this as a vector, you're using these two as the vectors. So the angle, you know, in between those two vectors is what you want, not this one. Okay, so then comma, and of course using the same values but with sine. All right. And so remember, what does this do for me? That gives me these two numbers in the component form of the vector. Remember, coming back to this. All right. So let's see what that ends up being. So the first thing I want is 65 times the cosine of 38. Let's see what that is. I want 65 times the cosine of 38. All right. And so that gives me 51.22. 51.22. And then I need the other one, which is going to be sine. Oops, take that off of there. Sine, 65 times the sine of 38. That's 40.02. All right, so there you go. So now we've got our two original vectors, and so now I'm going to have to take this and see if I can add those two together to get the resultant vector. So 61 plus 51.22 is going to be 651.22. Okay? And 0 plus 40.02 is 40.02. So that is going to be your resultant vector. That's going to be the resultant vector. Okay, so that's actually the vector of the direction that the plane is actually traveling with the wind affecting it. Okay? Now, what do we need to find from this resultant vector? We need to determine the speed of the airplane's flight. Well, remember, even though it's going 600 miles per hour, it's accelerating at 600 miles per hour, the tailwind behind it is going to make it actually travel a little bit faster than that. How much faster? Well, we need to figure out the magnitude of the resultant vector to figure that out. So that's what we'll do now. Magnitude of the resultant vector can be found by taking the square root of 651.22 squared plus 40.02 squared. So let's see what that turns out to be here. So we'll go square root of, right, 651.22 squared plus 40.02 squared, and then so we get our resultant magnitude, which is 652.45. Okay. Miles per hour. So that is the speed of the airplane's flight. Now, granted, this doesn't account for some of the physics of the, the aerodynamics and drag of the plane and the weight of the plane and, how many passengers are on it, is the weight higher or lower than it typically, all that kind of stuff. This is just straight using the two vectors as the only factor, in other words. Okay, so just kind of keep that in mind. All right, but as you can see, theoretically, with a 65 mile per hour tailwind that's at 38 degrees, off of the back of it, that should give the plane a boost of about 50 miles per hour. All right, theoretically speaking, ignoring all the other external factors. Okay, we have something else we have to answer, though. We want the angle also of the airplane's flight. It's not going to be going due east anymore because the wind is going to knock it off a little bit. How much? We can figure that out by going tangent of the angle is equal to B over A. What's the B? 40.02. And what's the A? 651.22. And so if I want the angle, I'll have to do inverse tangent to both sides, which means I need to find inverse tangent of this fraction, 40.02 over 651.22. And we can go back into our calculator to figure that out. And so let's go inverse tangent of 40.02 over 651.22. Okay, so that will give me an angle of 3.52, and that's in degrees. Okay. And so now, how do I take this and write it as a bearing, since we're using airplane flight? So I need to use that as a bearing. So kind of like the same bearing that was written out here for this angle, I need to write it in terms of how many degrees east or west of south. And so if my angle is off 3.52 from here, well then what I'll need to do is subtract that from 90 and write it like this. I'll write it as south, and then I need to go 90 minus the 3.52, which will give me 86.48 east. So it's 86.48 degrees east of south is the answer that you would be looking for. Yeah? All right? So remember, bearings are so many degrees east or west of north or south. All right? Because it goes off the north or south bearing. Okay? All right, so there you go. That's it.